So far in this course, we have gone through a lot of algorithms which are used for predictive analytics. We have looked into a lot of ML methods, where we can apply them and what benefits we get out of them. Let's take a quick overview of what we have learned so far. So initial stages, we understood what linear regression is. We used linear regression to predict stock index prices as a function of interest rate and unemployment rate. Then we moved on to classification based problems, where we used logistic regression to predict the probability of a person having diabetes using variables such as BMI, age, insulin, glucose level, and etc. Then we looked into techniques of decision trees and used decision trees to develop a solution for an electronics company to sell their computer games, for them to understand which group of customers should they be targeting. In our analysis, we could find that people with an age of less than 15 and having a gender of male are the person who are most likely to buy a computer game, and customers having an age above 15, whether they are male or female, are least likely to buy a computer game. Then we looked into the problems that decision tree has in terms of bias and variance, and we looked into techniques that can compensate for this bias and variance prevalent with the data. We looked into bagging, boosting, and application of bagging and boosting such as random forest and gradient boosted algorithm. Next, we moved on to algorithms such as KNN, with which we could understand that using the neighbors, we could classify clusters of data based on the assumption that similar data are clustered together. Then we looked into the algorithm of SVM, using which we could actually bifurcate our data set by creating a line between the data, and on each side of the data we assume that homogeneous group exists. And finally, we looked into topics of neural network, which kind of mimics the way neurons actually work in our brain, and using that technique, which uses inputs and weights and uses an activation function, we create the output. We saw the places in which neural networks can be used, for example in natural language processing, and so on and so forth. So in all of this discussion, we have looked into a lot of algorithms. A question that might come to you is when to use a particular algorithm. As we see that as we go from one algorithm to another algorithm, we do increase the efficiency of that algorithm. We increase the accuracy with which the model actually predicts the future. But is the most accurate model the best suited for your problem? Let's take a look into history first. Let's go back to the World War II scenario. In World War II, we all know about Tiger tanks. Tiger tanks were actually used by Germans. They were well renowned for their speed and agility. But on the other hand, English people had Churchill tanks. Churchill tanks were heavily armored tanks, but they moved very slow. So given a layman, he would always prefer a Tiger tank because it is fast, it is dynamic. But is that the real choice that you should be making? Well, you should be asking the question of why that particular tank was developed. While Tiger tanks were developed by Germans to enable the pincer movements of attack, which allowed for agility and fast pace of attack, it was well suited for what they wanted to do with that tank. And the Churchill tank, on the other hand, was actually used to provide cover for the infantry, and that's why it was designed to move slowly. So even though we may think that the Churchill tank, which is slow, may be inferior to the Tiger tank, but it actually served the purpose for which it was developed. So taking a cue from the story that we just heard, let's try to plot all the algorithms that we have learned so far in an X and Y plane, where X refers to the performance of the model and Y refers to the interpretability or the explainability of the model. As we increase in the x-axis, the performance of the model gets better, and as we increase the value in the y-axis, the interpretability of the model gets better. So here are the plots of all the algorithms that we have seen so far. So while linear models like linear regression, logistic regression are highly interpretable, but the performance is not as good as the other model. And on the extreme right, we have models such as XGBoost, deep learning and neural network models who have very high performance, but the explainability is not very good. They are essentially black box models. So can we assume that we should be always looking into performance? Well, no. Sometimes we need to understand and interpret the model better so that we can explain what features and how these features are actually impacting our output. In such a scenario, we should be preferring a model which is much more interpretable. It may lose out points on performance, but interpretability then wins over performance. And in scenarios, we are not bothered about the interpretability of the solution. We are much more focused on the performance. In that case, we should go to the extreme end of the x-axis and gain models which are high performing. So this is something that we wanted to discuss in this particular session, where we can say that of all the algorithms we have learned so far, none of the algorithms are absolute. Each of these algorithms serve a particular purpose. Now it's up to you to understand what is your purpose, which algorithm fits, and which business value you want to cater to. With that, I would conclude this session. It has been great interacting with you. Hope you had fun. Thank you very much.